This is number 13 from the integral test series homework. And the big giveaway here would be, when you look at these again, you've got to identify, first of all, apply the nth term test. Okay, as n goes to infinity, that denominator is going to get much bigger very quickly. The individual terms will approach zero, which means there is the possibility that this series will converge. Okay, again, doesn't really look like a geometric series. You might be able to do something with a comparison test here, which actually we haven't officially talked about yet. But if you're coming back and looking at this later, you know, there's some other things you might be able to do here. But again, the big giveaway, I can take the integral of that, and it's a pretty basic integral. And so as a result, if you recognize, hey, I can take the integral of the related function x over x squared plus 1 dx between 1 and infinity, go ahead and do that. So this is a reciprocal. Notice the derivative of the denominator here is 2x. That's very similar to the numerator. We're going to be able to treat this as a reciprocal function, and as a result, it's going to have a natural log. Okay? So again, if you're watching this from the outside, you'd probably do a use substitution here. I don't use use substitution in my class, but you're more than welcome to use it if you're not in my class doing this. Derivative of the inside function is a 2x. Okay, we have an x. We can bring that out here. We need 2x. So I can multiply by 2. I'm going to balance that by dividing out of 2 and factoring that out of the integral. Okay, so you reverse the chain rule. Derivative of the inside function is absorbed back into the function. The integral of a reciprocal is a natural log of whatever you took the reciprocal of. So it's natural log of the absolute value of x squared plus 1. You've got a 1/2 out front. By the way, first of all of our bounds here are positive. Second of all, anything squared plus 1 is always going to be positive. So we don't really need this absolute value here. Okay? And we're going to be evaluating this between 1 and infinity. Again, you don't really evaluate something at infinity because infinity is not really a number. So this is technically an improper integral. Technically, you're taking the limit of this as some variable approaches infinity. Okay, so we can substitute in here according to the fundamental theorem. We're going to sub in b, we're going to sub in 1, and we're going to subtract the 2. Okay, it's still going to be a limit as b approaches infinity. So that'd be of 1/2 ln of b squared plus 1. Then we'd be subtracting 1/2 of ln of 1 squared is 1 plus 1 is 2. Okay, that's a value. Okay, so we don't really have to worry about that too much. Anyway, if you substitute infinity in here, the natural log of infinity, if you think about the natural log function, of course crosses the axis at 1. It continues to increase slowly forever. So if you've got a natural log of infinity, this statement here is going to diverge. The other part of it doesn't even matter at that point. Okay, this is a divergent series because the indefinite integral diverges. Okay, so yet another example of how to use the integral test.